everyone. This side Mansi Mahindru, Assistant Professor in the Department of Computer Science. So for today, we're going to continue our topic, that is very important topic from advanced data structure, that is binomial heap. In my last video, I have already covered what is binomial tree and what is binomial heap, because we know in order to understand binomial heap, it is very important to get an overview of what is binomial tree, what are the different properties that need to be fulfilled in order to construct binomial tree, because binomial heap is only the union of all the binomial trees, just the combination of all the binomial trees. It is binomial heap. So if you haven't watched my previous videos of the properties of binomial heaps, then please go and watch that video first in order to understand this particular video in better way. So in last video, we have also covered some of the operations that we can perform on binomial heap. Like we have already covered first three operations, and in today's session, we're going to focus on the fourth operation, that is binomial heap union operation. And this is the most important operation of binomial heap, from which the questions are frequently asked in university exams, right? So we're going to cover this operation in detailed way in today's session. Now, what exactly this particular term means, what all about this operation is. So in union operation, we mean that if we have two binomial heaps, we have two different binomial heaps, and we want to merge these two binomial heaps together to make it one binomial heap. So at that time, when we are studying the properties of binomial heap, at that time we have studied that whenever we are constructing binomial heap, in that all the binomial trees should be in the increasing order, should be arranged in increasing order, and no two binomial trees can be have the same degree. So all these properties will definitely going to be violated when we're going to merge two binomial heaps together. So we have to find a way like how we're going to resolve these violations and how we can merge two binomial heaps in a single binomial heap. So we'll understand this particular operation with the help of example, because that's the most efficient way of understanding any concept. Okay, so for example, if we have two binomial heap, H1 and H2. Now what I want to do is I want to merge these two binomial heaps in one binomial heap, that is H, that is being denoted by H. Now, first of all, for this, what I need to do is I have to calculate the degree of each binomial tree. Now, in order to calculate the degree of each binomial tree, I have to count the child nodes of every root node. So starting from here, this particular node is of the order B0, because this particular root node is not having any child node, so degree is B0. This node is having one child node, so this binomial tree is of the order B1. This binomial tree is of the order B2 because there are two child nodes. Now here also we have one binomial tree of the order B0. This binomial tree is of the order B1, and this binomial tree is of the order B3 because there are three child nodes. So this particular binomial tree is of the order B3. Now we want to merge these two binomial heaps in one binomial heap. Okay, so we'll start merging here. We know that in binomial heap, all the binomial trees should be arranged in increasing order. So we have to start from degree B0. So we have to search, is there any binomial tree of the order B0? Yes, there is one tree of order B0. So we'll connect 12 here. Now we'll search, is there any other binomial tree of the order B0? Yes, there is one more binomial tree of the order B0. So we'll connect it here, 12, and here we have 18. Both are of the order B0, right? Now, there is no other binomial tree of order B0, so we'll start searching for B1. Yes, there is one binomial tree of the order B1, so we'll connect it here, 7, and here we'll connect it, 25. Now, is there any other binomial tree of the order B1? Yes, there is one more binomial tree of order B1, so we'll connect it here, This is 3 and this is 37. Right? Both are of order B1. We'll update our pointer. We'll search for B2. Yes, there is one more binomial tree of the order B2. So we'll connect it B2 here. 15. 15 left child is 28. Right child is 33. And here we have 41. Right? Is there any other binomial tree of the order B2? No, there is no. So we'll search for B3. There is no binomial tree of the order B3, but here we have one binomial tree of the order B3. So we'll connect it here. Here we have 6. We have here 29. We will have here 10. We'll have 44 here. 48. 31. And here we have 56. For 10 also we have one child node, that is 17, and I think we are done, right? So this is our resulting binomial heap. When we have merged two binomial heap together, we got this binomial heap as our resulting binomial heap. But here what we can see is that there are two binomial trees of the order B0. See, these two are of the order B0. These two are of the order B1. This is of the order B2, and this is of the order B3. But during the session when we have studied the properties of binomial heap, at that time we have studied that in binomial heap there should not be any binomial trees whose degree is same. Means there is no binomial tree in the binomial heap whose degree is same. But here we have this case. How to resolve this violation? For that, we have to understand some cases with the help of which we can resolve these particular violations. So these are the cases. These cases will going to help us in order to make our binomial heap fit from all the violations. Okay, so according to the case 1, it is saying that if the degree of x is not equals to degree of next x, then move a pointer ahead. What does it mean? What does this line means? Okay, so for now, we're going to read these rules, then we'll apply it one by one. Case 2 is saying if degree of x is equals to degree of next x is equals to degree of sibling of next x. First of all, we have to understand what does this degree of x, degree of next x, what does this sibling of next x means, where these terms are present. How we're going to identify these terms. So for that, we have to go to our previous slide. Right. So let's take one very simple case. See, if we are starting our operation from here, then this becomes my x, this becomes my next x, and this particular becomes sibling of next x. This becomes sibling of next x. So in the properties, we can see that if degree of x, we know what is degree means. Degree means the number of child nodes. For calculating degree, we just have to find the number of child nodes for a particular root node. Okay? So to understand these cases, we have to first understand all the terminologies that are used in these cases. So we know what is the meaning of degree, we know what is x, where this next x is present, where this sibling of next x is present, we all know this. So now we can understand these four cases very clearly. Case 1 is saying if degree of x is not equals to degree of next x, then move your pointer ahead. Case 2 is saying if degree of x is equals to degree of next x is equals to degree of sibling of next x, then also move your pointer ahead. Case 3 is saying if degree of x is equals to degree of next x, but it is not equals to sibling of next x, and the key of x is smaller than key of next x, then you can apply this case 3. Means what you can do is you can remove next x from root and you can attach to x. And same case we have for case 4. In this, just what difference is that if key of x is greater than key of next x, then you have to remove x from the root node and you have to attach it to next x. This is just the slight difference between the case 3 and case 4. If you haven't understand these cases now, but it's no issue, there is no issue. When we'll start with the numerical, you will understand all the cases very clearly. Okay, now let's start with the question. This is the same question that we have solved in our previous slides. We know how to merge these two binomial leaps together, right? So after merging, we got this particular binomial heap, right? Now we want to fix this binomial heap. We want to make it free from all the violations. So to make it free from all the violation, we have to apply those 4 cases on this particular binomial heap. So what we can do is, first of all, we will going to mark our x, next x, and sibling of next x in our binomial heap. So this becomes our x, this becomes our next x, and this becomes our sibling of next x. This becomes sibling of next x. Right? Now we'll check कि कौन सा केस यहाँ पर फिट होता है. Here, the degree of x is 0, degree of next x is again 0, and degree of sibling of next x is 1. So, according to the cases, which case is basically fit in this particular scenario, we have to check. So, let's go to the previous slide first and let's check कि कौन सा case यहाँ पे fit होगा. Here we have degree of x is equals to degree of next x, but it is not equals to the degree of sibling of next x. We're going to tell you which case will going to fit here. See, degree of x is not equals to degree of next x, but in our scenario, degree of x is equals to degree of next x. So case 1 is not appropriate for this particular scenario. If degree of x is equals to degree of next x is equals to degree of sibling of next x, but in our scenario, degree of x is equals to degree of next x, but it is not equals to sibling of next x. So it means case 2 is also not appropriate for this particular scenario. So either we can apply case 3 or we can apply case number 4, right? But for case 3, we also have to check if key of x is smaller than key of next x, then we can apply case 3, and vice versa. If key of x is greater than key of next x, then we have to apply case number 4. So for that, we have to check this particular condition also. So we'll check here. Degree of x is equals to degree of next x, but this is not equals to sibling of next x. So it means either case 3 can be applied or case 4 can be applied. But for that, we have to check whether the degree of x is small or degree of, the key of x is small or key of next x is small. So here we can see key of x is smaller than key of next x. So in this case, our case 3 will going to work in this particular scenario. So we'll see how case 3 actually works. In case 3, key of x is smaller than key of next x, then we have to remove next x from the root node and you have to attach it to x. Okay, then we'll apply this operation here. Now, once we'll apply case 3 in this particular question, what we can do is we have to remove 18 from root node and we have to apply it to 12. So it will become like this. As you can see, after applying case number 3, sorry, I have, this is just a typo error. This is case 3. This should be case number 3, right? So here what we'll do, the key of x is smaller than key of next x. So we're going to apply 18 here. We'll remove 18 from the root node and we'll apply here, right? Now after this, again, we can see this particular binomial tree is of the order B1. This is again of the order B1. This is again of the order B1. So means this binomial heap is not free from violation till now. So we have to apply more cases. So again, what will be there? See, let me take my pen first. Yeah. So now after this operation, this becomes my x. This becomes my next x. And this becomes my sibling of next x. right? Now here I can see degree of x is equals to degree of next x is equals to sibling of next x. Means all the degrees are same. So we'll go to our slide and we can see if degree of x is equals to degree of next x is equals to degree of sibling of next x, then just simply move your pointer ahead. Means we have to apply case number 2. So here we'll apply case number 2 and we're going to move our pointer ahead. Now this x, previous x becomes your, this x becomes your previous of x. Now our new x will be this, right? So we'll apply cases on this scenario again. We'll see this is x, this is next s, and this is our sibling of next x. Let me take my pen. And this becomes my sibling. Sibling. Now again we'll check degree of x is equals to degree of next x is not equals to sibling of next x. So we know when degree of x is equals to next x but it is not equals to sibling of next x, at that time we have to apply either case number 3 or case number 4. But for that we have to check the key value of x and next x also. Here, the key value of x is greater than key value of next x. So it means case 3 can't be applied. So here we have to apply case number 4. We have to remove this particular x from the root node and we have to attach it to the child node of next x. So let's see how it actually works. When we'll apply case number 4 here, what it will become? See, 7 is greater than 3. So we'll apply case number 4 and we'll remove this 7 from here and we're going to attach it here. We'll remove x from the root node and we'll attach it to next x. So same we have studied when we are watching the cases. So this is how actually it works. Okay, again we can see this binomial tree is of the order B1, this binomial tree is of the order B2, this binomial tree is of the order B2. Means again violations are not still resolved. We have to apply more cases here in order to get it done. So now this becomes, after this iteration, this becomes my x, this becomes my sibling, sorry, this becomes my next x, this becomes my next x, and this becomes my sibling of next x. Right. Now here degree of x is equals to degree of next x is not equals to sibling of next x. So either case 3 can be applied or case number 4 can be applied. But here we can see the key of x is smaller than key of next x. What does it mean? It means we have to apply case number 3. Means we have to remove next x from the root node and we have to attach it here. Means 15 will be applied here. Attach here. We'll see here. Case number 3, when we'll apply case number 3 here, it will become like this. As you can see, key value of 15 is greater than 3. So we have removed 15 from here. We'll apply 15 here. Sorry, it will, I'm so sorry, it will become, 1 second. It is 3. It becomes 3. And this is 15. This will become 15. This is 28. And this is 33. This is 41. Okay. And this particular is, this is 3. And this is 37. This tree will work like this. This is the tree. This is the tree. This is 3, right? Okay, now we'll see again. See, this particular binomial tree is of the order B1. This particular binomial tree is of the order B3. This is again of the order B3. Means we have, again we have 2 binomial trees of the same order. Means still violation is not resolved. So again what we have to do, we have to fix this violation with the help of cases. Now, what it will be there? It will become my x, this will become my x, this will become my next x, and this will becomes my sibling of next x. Right? So again, we're going to check the cases. So again, we'll apply case number 3 here. So we'll check. See, degree of x. So the key value of x is greater than key value of next x. Key value of x is greater than key value of next x. So what we're going to do, we're going to remove 15 from here and we're going to attach it here. See, one will do it. 1 second, let me take my pen. What we'll do, we're going to attach 15 here. 15 will come here. Now we'll attach like this, 3, then we have 28, like this. So like this, we'll attach this tree and we'll remove 15 from here. Right? Now, this particular binomial tree will become of the order B4 and this particular binomial tree is of the order B1. So we have two binomial tree of different degrees. So means all the properties are fixed. All the properties are fixed. No, there is no violation in the binomial heap. So we can stop our process here. And this is our resulting binomial heap. This is our final binomial heap. So in this way, we're going to solve the questions of binomial heap union operation. Now, if anyone asks what is the time complexity in performing this union operation, then we can simply say that the time complexity is O of log n. Why? Because we can see we have two binomial heaps. Each of them contains n1 and n2 nodes. But the operation that we are performing is only on the root node. Okay, means we are only traversing the root node. So means to traverse the first binomial heap, it will take log n plus 1 time. To traverse heap number 2, it will also take log n plus 1 time, and when we'll merge both binomial heap together, we'll get 2 log n plus 2, which is equivalent to O of log n, because we'll only take the dominating terms, we'll neglect all the small terms, so we'll only left with O of log n. So the time complexity in performing the union operation is O of log n. So that's all for today. In the next video, we're going to cover the remaining 3 operations, that are the extract min operation, decrease key operation, and delete key operation. And all these 3 operations are equally important for your university exams. So thank you all for your watching, for your patience. Thank you so much.